Hi, today we're going to be talking about 3.5 derivatives of trigonometric functions. We're going to be finding what is the derivative of sine and the derivative of cosine. We're going to talk about what simple harmonic motion is. We're going to talk about jerks, or really just jerk, and we're going to be looking at the other trig derivatives that there are. What I'd like you to do is go ahead and go into your graphing calculator. You can set your window up as described here from negative 2 pi to 2 pi and negative 4 to 4 for your domain and range. Graph on y1 the sine function, and then on y2 use the function n derivative, it's n der, of the sine of x, meaning it's going to graph the derivative of sine. Now, when you graph the derivative of sine, be very patient. It will take a little while longer because each of the points it's basically finding the derivative of, so it just takes it a little bit longer to graph. So just be patient with it. Hit pause, answer all these questions, and we'll see what you find out. Go ahead and hit pause. Okay, let's see what we have. Hopefully you have some sort of graph that looks like this, where the blue graph is the one that we started with. So we're looking at this blue graph here, and the blue graph is the sine function. And hopefully you notice that when you take the derivative of sine, you get the red function here, right? And you noticed, really hopefully, that the sine or the derivative of sine is equal to the cosine of x. Okay, so hopefully that's kind of what you noticed. And also I'm hoping that you took the cosine function, and if we were thinking about the derivative, and I'll kind of do this one with you. If I start here at 0, what is the slope there at 0 of cosine? Well, the slope of cosine is 0. So I would come into here and I'd draw a point there. Then I'd come over to this point on the graph. That looks like it'd be a slope of about -1. So I'd come straight down on that to -1, and I'd put a dot there. Okay, then hopefully you look over here, that's a slope of 0. So there, I'm back to 0, which should be there. Alright, and we kind of continue from there. It goes up to +1 here, so I'm at +1 there, and so on. It will repeat itself just as we go, like, oops, I can't get rid of that one. Just like that. So hopefully you notice that it makes this wave, and I'm hoping that that wave you understood to be, so then we take the derivative of cosine is equal to, if you notice that is just the negative sine of x. So the derivative of sine is cosine, the derivative of cosine is negative sine. So that's what we have written here. Derivative of sine is cosine, derivative of cosine is the negative sine. So remember, we're just talking about those slopes. So the slope function for sine is cosine. The slope function for cosine is the negative sine function. Simple harmonic motion just shows if you're describing like a weight on a spring. So think of a slinky and tie a weight to it. Hang the slinky from a balcony, and then go down and pull on the sling and then let go. It will go up and down and just keep bouncing up and down. Well, let's just pretend that we lived in physics land where there was no air resistance, and that spring would just keep on going forever. Okay, once you add that initial force to it and then let go, it should continue forever. So if we had a position that was described as s here, where we have 5 cosine of t, right? The velocity is just the derivative of that position function. Like always, velocity is just the rate of change of position. How fast is the position changing? So we know that always velocity is the derivative of position. We also know that all acceleration is how fast is the velocity changing. So the velocity changes, so it's the derivative of the velocity function for acceleration. So you can see this is a very simple example of what simple harmonic motion shows. If we have a position function, we can calculate the velocity function, we can calculate the acceleration function. Well, let's just say someone in the class asks, well, what is the derivative of acceleration? Well, that student would be a jerk. Just kidding. Not really. I like that you ask questions. Oh, that was a bad joke, sorry. I'm going to get even worse here in a second, though. Jerk is the derivative of acceleration. So if we're trying to find out how fast is acceleration changing per unit time, that is a jerk. Okay? So if I ask you that, you just answer jerk. So next time I ask you, what is the derivative of acceleration? Jerk. Okay, so you can kind of practice that. Also, I just wanted to let you know, what is dA dt colon dash and then a straight line there. So what is that? That would be the jerk, and that's a face if you're typing. So that's a jerk face. Okay, sorry, bad joke again. Yeah, ladies, just one last terrible joke. If you had your homecoming date ditch you or something, you can just go call them the derivative of acceleration. So try that out. See if it works next time. Instead of like slapping them, just say you're the derivative of acceleration. Anywho, we also need to look at the other trig functions. So let's look at the derivative of tangent. The derivative of tangent is the secant squared function. The derivative of secant is secant times tangent. The derivative of cotangent is the negative cosecant squared function, and the derivative of cosecant is negative cosecant cotangent. Notice that everything, when we're taking a derivative of something that starts with a c, it is the negative. When it was the derivative of cosine is the negative sine. Derivative of cotangent is the negative cosecant squared. Derivative of cosecant is negative cosecant cotangent. So, a lot to memorize. It will get better the more that you use it. So, speaking of that, why don't we start using these? Go ahead and give this a shot. Find the derivative of 2 sine x minus tangent of x and see how you do. Hit pause. Okay, so dy dx is equal to, we can ignore that 2 and just put it in front, 2 times d sine of x dx minus the derivative of tangent of x in terms of x. So I would just take, this would go to equals 2 times the derivative of sine is cosine of x minus the derivative of tangent is the secant squared function. So that is dy dx for this first one. Okay, so go ahead and try the second one and hit pause. Alright, so the dy, I'm going to write it actually this time just to change it up a little. Y prime, the derivative of y, is equal to, okay, so we've got two functions, x and secant x. So we do the product rule, which is first times the derivative of the second plus second times the derivative of the first. So if I call x equals a and secant x equals b, I would do first times the derivative of the second plus second times the derivative of the first. So if I do that, I have y prime equals first, that's x, times the derivative of the second. Derivative of secant is secant times tangent plus second, the second is the secant of x, times the derivative of the first. Derivative of x is just 1, so we can just leave it like that. Okay, give this one a shot and hit pause. So this one we've got the quotient rule, so low d high minus high d low over low low. So let's say that low we'll call cosine of x, we'll say is a, and 1 plus sine of x is b. So this is going to combine a couple of things, so we'll just have to be a little careful. But anyway, we know that y prime is equal to low d high minus high d low over low low. Okay, so let's give that a shot. B is low 1 plus sine of x, low d high, the derivative of cosine is negative sine, minus high cosine of x, d low, the derivative of 1 is nothing, it goes away, plus the derivative of sine is cosine, all over low low, plus sine of x squared. Okay, you can really pretty much leave it just like that for now, unless you're going to have to use it or answer a multiple choice question. That's probably where I'd stop. So we've got this weight. We were supposed to write an expression in terms of the velocity and acceleration, if you remember. This is the position equation, and velocity is just the derivative, so s prime, which equals velocity, is equal to 7 times cosine of t is negative sine of t. So there is the velocity equation. When we're writing an equation for acceleration, we know that s double prime equals v prime, which equals the acceleration. So the derivative, or the second derivative of position, is acceleration, or the derivative of velocity is acceleration. So the derivative of negative sine of t, derivative of sine is cosine, so this just becomes negative 7 cosine of t. Now, what's the derivative of acceleration? Jerk. Okay, just throwing that in there. But it should get us back to a positive if we did that. What's the jerk? I don't even remember what letter. We'll use J for jerk. Equals the derivative of cosine is negative sine, so I'd get rid of that negative. It'd be 7 sine of t. And then notice the derivative of jerk just puts us back. If we took the derivative of this, j prime, this was s triple prime. Okay, if we do a fourth derivative with sine or cosine functions, it gets us right back to where we started. So kind of interesting little pattern there. that you might like. Okay, last little problem here before you're done for the night. Find the points on the curve tangent of x between negative pi over 2 to pi over 2 where tangent is parallel to the line y equals 2x. So let's just think about those words. Parallel to the line, meaning it's going to have the same slope. So we're really looking for when does the tangent function have a slope of 2, because we know the slope of y equals 2x is 2. So we just need to take the derivative of tangent. So y prime equals secant squared of x. And we're just trying to find out when is this equal to 2. Okay, so I have a hard time seeing secant squared written like that and being able to solve algebraically, so I have to rewrite secant squared as secant of x squared equals 2. Now I can go, okay, I know this is the square root and square root, so that leaves me the secant of x equals the square root of 2. And from there I can change secant to 1 over cosine of x equals square root of 2. But that's hard for me to understand, so let me just flip that and make that when is the cosine of x equal to 1 over the square root of 2. But that's an improper fraction, so I'm really asking multiply this by root 2 over root 2, and I get what this is really asking is when is the cosine of x equal to square root of 2 over 2 on the domain pi over 2 or negative pi over 2 to pi over 2. So if I'm looking at that, when is cosine equal to root 2 over 2? Well, I know root 2 over 2 is when we're at those 45 degree angles, which would be at x equals negative pi over 4 and at pi over 4. So those are the points on the curve between negative pi over 2 and pi over 2 of when the tangent of x has a slope of 2x. Now if I look really quick at the tangent function, and I'm looking at where is the slope equal to 2, well, it's hard to tell on here, but I'm guessing if this is 0.5 and that's 1 right there, that's 2, 3, 4, that looks right based on the scale. The hard part is to see where are all of these going. So I've got let's see, pi over 2 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 away. So I need to go 1, 2, 3, 4, 5, 6, 7.5. I'm talking about this point right there. Okay, when is that slope? What is that slope? Well, again, it's hard to tell exactly with this line, but there and here are where we're talking about. If you were to take 2 points on those lines, I bet you're going to find that the slopes are pretty darn close to having a slope of 2. As you go over 1, you go up 2. So hopefully that kind of makes a little more sense with the little visual there. Maybe you can adjust your graph if you need to make more sense so that it looks steeper, because right now it looks pretty flat, but that's just because of how we're zoomed in. Well, I hope this helps, and I'm excited for all the questions and fun we're going to have tomorrow. Thanks. Have a great night.